Hello students, today we are going to study electrostatics. This topic is very strange for some and it is quite good for some other students. But if you take it seriously, if you get interested into it, it is quite enjoyable. So we have some questions, some basic questions regarding to this related to this concept, and similar questions you might see in very recent IIT questions. In this I have collected some questions and I have also collected one question that I haven't even touched. So I will try that along with you. That would be the last question of this session. So stay tuned with me through the whole session and we will do it together. So let us start with the first question that we have. It is related to electric flux. As you know that electric flux is the product of area vector times the with the dot product included, means area vector with electric field vector. So flux is a scalar quantity and it is equal to the dot product of two vector quantities, area vector. Area is not a vector quantity, but when you say area vector, that is a vector quantity, and electric field. So here in this question which says which already giving us an example, you have a 3D structure here, x, y and z axis, and in that you have a surface whose corners are given as the x, y, z coordinates, and using these coordinates you have to find out the flux that is passing through this plane, this part of the plane. So here let us read it together. Consider an electric field E vector equals to E naught x, that we call it unit vector here, where E naught is a constant. Okay, the flux through the shaded area due to this field is. So this is a uniform electric field that will not leave us stranded working out some kind of integral. So this is kind of easy question, but we have to find out how we get to find the area vector, and that is a dicey part here. So to do that, first let us try to understand the situation and let us see how we can find the overall flux. So here let us see, this is our coordinate axis just like that, and here we would be having A, again A and again A. So somewhere we would be getting point A and 0. Here I am taking z axis as in this figure here, z, y and x. So if you are taking a point from z and x axis, z or z axis, x axis and z axis, so you would be getting A, 0 and A. That means x coordinate is A, y coordinate is 0. We are considering that we haven't moved anywhere up or down in the y direction. Z, we are getting A. So what we are having here in this plane, the coordinates of this plane. So consider it this way, this plane has the lower coordinates, means the base coordinates of this plane is 0 0 0. First thing, that would be the origin itself, 0 A 0, that means it is on y axis. The second part, y axis, from the origin move a distance here, this is your y axis. So you can see that the base lies on y axis and it has a length A. Now let's consider its height. You can see that its height goes somehow slant upward. It's not exactly on z, it's not exactly on x, it's on xz plane. So it would be something like this, means it is, and it is inclined to both the axes equally, a and a. So you can say that it is making 45 degree with the xy plane, xy plane being the base, or in the same way you can say that it is making 45 degree with the zy plane or yz plane. And another coordinate, another point coordinate is AAA, means all the axes have a point in it, all the coordinates x, y, x coordinate, y coordinate and z coordinate, all the coordinates are a. So you would be having such a condition that it is a rectangle which is tilted 45 degree with respect to xy plane and the yz plane. Now, can we find the area of this rectangle? Yes, we can. So the length of this rectangle, the base length is a, the slant length that you can find is a square plus a square plus 0 square the whole under root, that would be a root 2, and this part is a, so the area is a square root 2 or root 2a square, whatever you write. Now if you are projecting this plane onto yz axis, and why we are projecting it onto yz axis? Because the area vector is along, area vector has to be along x axis in which the electric field is oriented. Now we have to find the area along x axis, because we would be working, simply write it this way: flux is equal to electric field dot product area vector. Now area is some vector is making a direction somehow like this, so it is making a downward 45 degree direction, so you can say that area is this and its direction is 45 degree with the x axis. So we can say that the flux is equal to, what was the area? A square root 2. What was the electric field? E naught E naught, I am just taking the magnitude, direction is x unit direction, unit vector, dot product area vector A square root 2. Now when we are calculating dot product, the angle between the vectors is, we are using the cos of that angle. So cos of 45, that gives us E naught A square root 2 times cos 45, cos 45 1 divided by root 2, that gives us E naught x square, E naught A square, I am sorry. Okay, so let us go back and see if we have a right option, a relevant right option, and yes, we have one of this, C E naught A square. So can we do it a little more easily in some way that makes more sense in a general way? So yes, I have a way. You might find that more sincere way as well. So you can visualize this plane, by which the way I have explained it, it is a rectangle which is tilted 45 degrees from the xy axis. So it is making a 45 degree with xy axis, its length is a root 2 and its width is a. So if you find its projection to the yz plane, why on projection yz plane? Because we have to multiply the area vector of this plane with the electric field which is directed in the x direction. So we need to find its projection on yz plane. So the projection would be simply if we drag this line here and project on z axis and same on this line on yz plane. So wherever it touches, we would be getting another rectangle, and by coincidence we would be getting a rectangle whose edge length is a. So both edges are of the length a, so we have a square there. The length of the area of this square is a. The electric field, area of is a square and the electric field is E naught in magnitude. So multiply both vectors, E naught times a square, E naught a square, that's we are getting here. So you can use any methods. One method is general visualization and another is pure mathematical. Whatever method you fit fine, you can go for that and find your answer. Whatever you use, answer would be this. So let's go ahead and see what question we have next. So again we have another question. It is quite related. If you have studied a little bit of about spherical capacitor, you might have studied this concept, but here we are not studying capacitor, spherical capacitor, but a basic concept of that. So whenever we encounter a sphere, metallic sphere, you can say that the electric field inside the sphere, whatever charge is there, the inside because of this sphere would be 0. And I am talking about the spherical shell, sorry, I did not make it clear. Spherical shell. So if some point is inside that shell, the electric field because of the charge residing on that shell would be 0. Now if we have another shell inside that original shell and we are talking about a point in between the boundaries of the shell, then we would be getting the electric field because of the inner shell but no outer shell. This can be explained by the Gauss's law, you know, that if you have a charge q inside any Gaussian surface, it may be spherical, it may be cylindrical, whatever surface is there, if you find the net flux, and flux that we just came across is the product of area vector times the electric field. So the flux through the whole surface is equal to the charge divided by epsilon naught. So now consider the spherical thing, the spherical shell thing that I just discussed. So if you have a spherical shell on which there are some charge distributed somehow like this. So the distribution is throughout uniform. Consider this as a metallic shell. There would be some electric field outside, you can assume. It might be uniform, it might not be uniform based on the distribution of charge, the shape of, if the shell is uniform, obviously it would be uniform, but if it is not completely spherical, the electric field may not be uniform. Now, what about any point inside the sphere? At this point, there will be no electric field. Now, if we introduce another shell inside there, would there be an electric field on this point? You can say that it has some charge, means if we are given that there is some charge, you can say, since if we draw a Gaussian surface passing through this point, then this, what do we call, the total flux passing through this would be this times this, right? Sorry, this charge divided by epsilon naught, and there would be some electric field, right? And that's true. But if we are considering the Gaussian surface through this line, means exactly on the plane of this surface, this outer shell, then we will not have any electric field, because the electric field through a metallic body, bulk of the metal, is 0, because metals and all types of conductors distribute the charge distribution among throughout its body in such a way that there is no electric field in between the masses, or is say the bulk of the metal. So, to do that, and let us say I can explain it in a better way. Let us say this was the spherical shell. I have made it thin. Now say this is the point where there is a charge Q. So, if I consider this Gaussian surface as this dotted line, you can say that there is definitely an electric field E, because there is a charge Q. But as I told you, through the metal bulk there is no electric field possible. Then there must be some charge Q here that is cancelling out, means inside this boundary, this Gaussian surface, the net charge should be 0. Then only the total electric field is 0, or the flux is 0. And that is possible only if we have some charge minus Q on this surface, because we know that at this point, or at this body here, we have plus Q. So, there must be some minus Q, and this minus Q is there because it has been induced by this charge, and to accommodate this minus Q, another charge develops here, plus Q. So, in that sense, whatever metallic structure you arrange, the inner charge of obviously and finally gets induced on the top of the metallic body, however arrangement you do. So, if you have kept this part neutral, this charge is reflecting here. If somehow you charge this by negatively or positively, you will definitely have an equal negative charge here, or opposite of this. If you put here negative charge, you will get a positive charge here, and finally you will have a charge here, such that if you have induced no charge here, this will be simply plus Q, or opposite of this. So, let me give you an example, and then we will come back to our question, and that after getting this understanding, that question will be very easy to solve. So, let's say there is a spherical shell which is having a charge Q1 and another spherical body which is given a charge Q2. If this is a positive charge, this whole shell has been given a charge Q2, and this body that somehow getting inserted inside the shell has a charge Q2. Then what will be the final distribution of charges on the three surfaces? Which three surfaces? First, this metallic surface. All you know that metals have charges on the surfaces. It doesn't distribute throughout the volume. All the charges would appear on the surface. So what would be the total charge on this surface? What would be the total charge on the inner surface, and the same on the outer surface? So to work it out, obviously this is not affected by any internal forces or anything any electric field from outside, because if this shell has some kind of charge distribution, that will not affect any internal part, right? So this will obviously will be having Q2 charge on its surface. Now if we consider the microscopic part here inside the bulk of this shell, you can say that there is no electric field throughout the cell. That means for the Gaussian surface that is passing into the shell, inside of that there is net charge equal to 0. If the net charge is equal to 0, that means the internal boundary of this outer shell is equal to the negative of this charge. If it is Q2, we would be having minus Q2 inside. Now to accommodate minus Q2, we would have to have another Q2 on the outer boundary plus the already existing charge which was Q1. So outer boundary will be having Q1 plus Q2. This is what happens when you insert one charged cell into another. So this is what the concept of shells, conducting shells with charges. Now let's go back to our question and read it together. Let's see if we can do it by the explanation I have just covered. So it says 3 concentric metallic spherical shell of radii r, 2r and 3r. So see this image here, it has 3 shells, metallic shells, and those are sphericals, r, 2r and 3r, and they have charges Q1, Q2 and Q3. It is found that surfaces charge density on the outer surfaces of the cell are equal. Okay, this part is to be noted. It is found that the surface charge densities on the outer surfaces of the shells are equal. Then the ratio of the charges given to the shells Q1 is to Q2 is to Q3 is. So we need to find the ratio of Q1 is to Q2 is to Q3. Now consider what we just discussed. Here we have 3 concentric circles. Start from the inner one. Inner one has charge Q1 and it will not be affected from the outer bound, anything out of it. So it will remain Q1. So it will have some charge Q1. Now consider the inner boundary of the second shell. inner boundary would have opposite charge because of the induced charge, because the charge induced by this enclosed charge. So, minus q1, it already had q2. So, to accommodate the outer shell surface would have q1 plus q2. Now, we have our third shell. If we have q1 and q2 here, we must have minus q1 and q2 in the inner boundary of this shell, minus of q1, q2 plus q1, but the total charge is q3. That means that outer shell, outer boundary of the outermost cell would be q1 plus q2 plus q3, and this thing has already been shown here, the charge distribution. Now things are getting little bit clearer. Now we will discuss the charge densities on the outer surfaces of the shell. So, inner surface has charge q1 and its area is pi r square, 4 pi r square sphere. So, let us discuss the charge and density on the next page. We do not have space here. We know that charge density, let us say charge density would be sigma, something like that, sigma 1, and we know all are equal, sigma 1 equals to sigma 2 equals to sigma 3. Now, if the all charge densities are equal, that means total charge on the outer surface divided by total area is equal for all the three. Let us see. For the innermost shell, the total charge is q1 divided by 4 pi r square. For this one, we had outer charge q1 plus q2. Divided by 4 pi 2r, the square of 2r, that would be 4 pi times 4r square, that is 16 pi r square, and it is again equal to q1 plus q2 plus q3, that is the charge on the outer boundary of the outermost shell, divided by what? The surface area of the outermost shell, and that was 4 pi times square of 3r. That would give us 4 pi times 9r square, that is 36 pi r square. Okay, we can solve it out. Let us first solve this thing. We would be getting pi 4 q1. If you solve only this part, 4 q1 equals to q1 plus q2, or you can simply say if you subtract q1 from both sides, you would be getting q2 equals to 3 q1. We get this part here. Now say q1, this compare these two, we are getting 9 q1, because if you cancel out 4 pi square from both sides, we still have 9 here and nothing in denominator here. So, that would be giving us q equals to q1 plus q2 plus q3 divided by 9, or in other words we would be say 9 q1 equals to Q1 plus Q2 plus Q3. Now we already know that Q2 is equal to 3Q1. So this 9Q1 is equal to, or let's leave it as 9Q1, Q1 plus 3Q1 is Q2. So let's convert Q2 into 3Q1 plus Q3. That gives us, take out all the Q1s on the one side. So 9Q1 minus 4Q1, that is 5Q1, is equal to Q3. So Q1 is to Q2 is to Q3 is equal to Q1 is to 3Q1 is to 5Q1. That means you can easily find out the ratio is 1 is to 3 is to 5. Okay. So let's see if we have a right answer among the choices. Yes, we have. I hope this is clear, and that's why I have explained a lot before that to make the shell structure and the charge distribution among itself. Okay, now let's move to another question, and meanwhile you can always post your comments if you have any doubt. Now this is some kind of error finding part, or say the right statement finding part. So this is quite theoretical, but each option that we are looking at are having different concepts. So but still all of them are from electrostatics. So let's read it together and see which one we can eliminate and which one we can say is right. If the electric field due to a point charge varies as 2r to the power 2.5 instead of r square, then the Gauss law will still be valid. Okay, so Gauss law is valid for our when the electric field varies as r with r square, means the square of r. But would that be same if we have something different than this? So let's consider a Gaussian surface, spherical Gaussian surface for a point charge, and this Gaussian surface is suppose r distance away from the point charge. So the area of this Gaussian surface would be 4 pi r square, and this charge is, let's say, q. This according to Gauss law, the electric field is constant. We are considering flux by the Gauss's law. The total flux through this surface is q divided by epsilon naught. And because of this q divided by epsilon naught, the flux is this, can we say that area, flux per unit area, flux per unit area is equal to q by epsilon naught divided by 4 pi r square. That gives us q divided by 4 pi epsilon r square. Okay, so this gives us that r square means electric field, this whole flux divided by area is electric field, if electric field is uniform, right? And it is uniform because the electric field in all the direction is would be same for a point charge. So electric field is equal to Q divided by 4 pi epsilon naught r square. So if we had something like electric field is equal to r to the power 2.5 here instead of 2, then this quantity, this electric field that we found using Gauss law would be different from the actual electric field. So that's why this is not a right way. Gaussian law would not be valid in that case, which is a fictitious case. So this is not true. Now let us read the second part. The Gauss law can be used to calculate the field distribution around an electric dipole. Okay, what is electric dipole? Electric dipole are two charges of equal and opposite equal magnitude but opposite polarity spaced away from each other with a small distance. Now consider a Gaussian surface outside, suppose it is a spherical area. So it will give us net flux as 0. Using this, can we find anything about the electric field? I do not think so, because if we consider this and divide by the area, we would be getting the electric field as 0. The same would be the case if we have a cylindrical structure, cylindrical Gaussian surface, that would also give us a wrong input. The only implication we could do is by making a Gaussian surface around them, but that too will give us the electric field for this direction and no other direction. So we can say that Gauss law is not useful to find the electric field distribution for a dipole. So that option is also wrong. Yeah. Let us see option C. If the electric field between 2 point charges is 0 somewhere, then the sign of the two charges is the same. Okay. Let us see. Consider two situations. In first situation, the charges are of different polarity, means one is positive, another is negative. This is a positive charge, this is a negative charge. Now consider any point here, exactly joining the two bodies, charged bodies. So consider the point somewhere in between. Let's say this is the point. Again another point, another point, another point. For all the points, the electric field by this charge outward, by the negative charge inward towards it. So here means again parallel to it in the same direction. For this as well, outward by this, inward by this, outward by this, inward by this. So for we are getting no such point in between the charges where the electric field could be 0, net electric field. Now consider two positive charges. So we are considering one point which is closer to one charge. We are considering both the charges have equal magnitudes. So let us say it is closer to this point and this body. So magnetic field, electric field by this charge would be greater, by this would be smaller because the distance from this left one charge is more, distance is more, so electric field would be more. If we consider the point to be here, the electric field by this one is smaller, by this one is greater. So net electric field is towards that, and for that is here. But if we get closer somewhere in between, we will have a electric field by both the both the charges equal to each other, and both are opposing each other. That's why they will get a point where the net electric field is 0. Now consider the same for negative charges. Obviously there would be electric field towards themselves, the same scenario would be there, and somewhere you will get a point where the net electric field is again 0. So yes, this is a right answer, this is a right choice. Let us see if D is right or not. The work done by the external force in moving a unit positive charge from point A at potential VA to potential VB is VA minus VB minus VA. So the work done by external force in moving a unit positive charge. This was important, which the part that I have underlined. So let us see what is happening here. So there are 2 points, one point A, another point B. The potential of this is VA, the potential of point B is VB. The electrostatic potential energy associated with this point for a point charge, a unit positive charge, that is you can say 1 coulomb charge, would be VA times unit charge. You can simply say, let us say that is Q, positive Q. So electrostatic potential energy for this point is VAQ. Electrostatic potential energy for this point would again be VB times Q. Now the work done from moving from here to there, so would be final electrostatic potential energy minus initial. So this minus this, VBQ minus VAQ. We can say this is equal to Q times VB minus VA. Now we just said that we have a unit positive charge, so we can say that Q is plus 1. Sorry, did I say VB here? Sorry, that's VA. So unit positive charge Q is plus 1. So we can rule it out, rewrite it as VB minus VA. Let us see if it was the right expression. VB minus VA, yes, it was right. So both statements C and D are correct. Okay, I had kept some question to try with you, but because of the time crunch I cannot explain that to you. I want you to have a look at it, and after some time we can discuss it together. So this is about two charges is equal to Q are kept at distance at x equals to, let me write it something like this. This is point A on x axis, this is point minus A, and here there is a charge Q. Here's another charge Q. Here's another charge Q2, Q by 2. Oh. So you can see that the force by both the charges are on the opposite direction and both are equal. By symmetry you can say that net force is 0. If we move according to the question, if we move it slightly up for y, what will be the net force and how is it related to y? Like, is it related to positive y, means is it proportional to positive y, it is proportional to negative y, is it proportional to 1 by y, and is it proportional to negative 1 by y. So you can find it out by making approximation. I want you to work it out, and hopefully we'll discuss the rest part of it in the next some sessions. Okay, that was all from my side. See you again in some next session. Until then, keep learning. Bye bye.